So, so far we've kind of explored how a single muscle cell contracts, and we said it's basically that you've got thick and thin filaments within myofibrils that slide past each other, and the sarcomere shortens. But what has to happen before the filaments can slide? What's actually the very first step? Yeah, the nerve impulse, definitely. So, this section is really about what's a nerve impulse, what actually is that, and how does it cause the filaments to slide. So before we get into that, just a little bit of terminology here, a little bit. So the first thing we need to understand is what's a motor neuron. And a motor neuron is actually a neuron that travels from the central nervous system to the muscle. So this is a neuron that travels from the central nervous system. And by the way, I'm going to write CNS for that, abbreviate it. The central nervous system means the brain and the spinal cord. So it travels from the brain and the spinal cord to the muscle. This is a motor neuron. It's a cell. Okay, so again, a motor neuron is a, is a neuron that travels from the brain or the spinal cord, the CNS, to a muscle. Okay, so this is a type of cell. Now, the motor neuron isn't your typical type of cell. So it's got like a body to it, which has a nucleus, but then it has this long process that sticks out and travels to the muscle, and that's called an axon. So the axon is the part of the neuron that extends from the CNS to the muscle. So this is a part of the neuron. Yep. Brain and spinal cord. Oh, sorry.
Central nervous system.
Thank you. Central nervous system, yeah. Now, usually motor neurons only have one axon, and the axon is what the nerve impulse is traveling along. So this is where the nerve impulse travels. And there's usually only one. So I'm going to show you a picture of one in a minute. Hopefully it'll make more sense. The next part is a motor unit. So a motor unit is one motor neuron, and all the muscle cells it stimulates. Sorry. Okay, so this is one motor neuron, and all the muscle cells it stimulates. Now, when you get to the very end of the axon, so remember the axon's traveling from your brain and spinal cord all the way out to the muscle, the very end is called the axon terminal. And then the last thing is the area where the neuron and the muscle cell meet is called the neuromuscular junction. Okay, this is the meeting place. Kind of like the junction between 93 and 95, like it's a meeting place. So let's take a look at what this looks like. Might make more sense. So here's a picture, and you can see you've got the spinal cord here. So remember, that's part of the CNS, central nervous system, the spinal cord. And in the spinal cord are motor neurons. But what is in the spinal cord is the cell body, so it doesn't really show you it here. But there'd be the cell body of the motor neuron. And then the red and the purple are the axons. So they're leaving the CNS and they're traveling to the individual muscle cells. So here you've got skeletal muscle cells, and you can see you've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So remember, each of these long things is a skeletal muscle cell. Remember, they're long and skinny. And then you'll see that the axon will split like that. It splits. And at the end of the axon, what's that called, the end part? The terminal, right, the axon terminal. And yes, it is also the neuromuscular junction. So do you remember, what's the connective tissue that surrounds an individual muscle cell called? Endomysium, right? So that endomysium insulates all these skeletal muscle cells from each other. So if one gets stimulated by a nerve impulse, the next one doesn't get stimulated. They're insulated. So each muscle cell has to have its own axon terminal going to it. Now, if you notice, just here for a minute, here you've got a bunch of muscle cells. Remember what a bunch is called?
A fascicle.
Yep, and what's the connective tissue that goes around a fascicle? Perimysium, right? And then here you've got a bunch of fascicles and then some more connective tissue. What's that called? Yes, epimysium, good. So anyways, each of these muscle cells has to have its own axon terminal. So if you notice, a motor unit, remember, is one neuron and all the muscle cells it stimulates. So how many muscle cells does motor unit number 1 stimulate? 2. Yeah, 2. See, 1, 2. Just 2. How about motor unit 3? Motor unit 2? 3. 1, 2, 3. So motor units can stimulate a few or a lot of muscle cells.
What is the yellow thing at the top? Is that the motor unit?
Oh, that's the spinal nerve. That's what spinal nerve looks like. We'll get into that a little later. So motor units can be big or they can be small. Here's another close-up of this. So if you look at this, there's some words on the left there, and you're supposed to label the picture. But imagine way up at the top somewhere is your spinal cord with the motor neuron in it, and coming down from there is the axon. So actually this is supposed to be the axon right here. That's the axon. And you can see the direction of the nerve impulse. They've got little arrows here showing you the direction. Oops, sorry about that. Now what's this called at the end of the axon? Right, so we've got the axon terminal, which are these little things here. Right, that's the end of the axon terminal. And then, of course, this whole thing is the muscle cell. You can see the nuclei. So what are these things then inside the muscle cell? Yep, that's the myofibrils. So you'll notice here that where the axon and the muscle cell meet, that's the neuromuscular junction, right there. That's it. Now, I don't know if you can tell, but do these two actually touch? No, they don't. There's actually, it's hard to see, but there's a space, so they don't really touch. If we took the axon terminal here and we expand it, so it's huge, you could look inside it. So this is also the axon terminal. right here, you can see there's lots of mitochondria in there. These are mitochondria. And then you'll see these other little things. They're like little vesicles. These are actually called the synaptic vesicles. Okay, the synaptic vesicles. So at the end of these axons, you've got these vesicles with something inside them, little green balls. What's that? So a little bit more terminology here. A synaptic vesicle. Well, you saw what it looked like. It's actually a vesicle, but what's inside this one is something called acetylcholine. And acetylcholine is abbreviated, by the way, ACH, so you might see that abbreviation. Acetylcholine is actually a neurotransmitter. I don't know if anyone's heard that word before, but a neurotransmitter is a chemical that carries the nerve impulse to the muscle cell. That's one way, at least, to think of it, kind of as a chemical that carries the nerve impulse to the muscle cell. So we're going to see later, we're going to define it a little better later, but right now that's probably a good way to describe it. So there's one more process I have to, one more word I have to define, which is exocytosis. You might have learned this in biology. I don't know if anyone remembers it. It's a cell transport mechanism.
It exits the cell.
Yes, how does it get out?
By, like, at an end, it doesn't have like a area.
Does anyone remember what? Yep, you've got vesicles. So let's say you've got a cell like this. Here's a vesicle. And so we have something inside it. So how does this stuff get out?
It pushes itself out next to the cell membrane.
Yeah, this is going to move over like this. And when it does, okay, so I'm going to go, it fuses with the cell membrane like this. It fuses with it. And then it releases its product outside. Remember that exocytosis?
Yeah.
Endocytosis would be if the cell, yeah, surrounded something and kind of had it inside as a, got it inside to a vesicle that way. So one way to think of exocytosis is the vesicle fuses with the plasma membrane and releases the product to the outside. Okay, so that's exocytosis. The vesicle fuses with the plasma membrane and releases its product outside the cell. Okay, so then how does the nerve impulse, or what's going on with that nerve impulse anyways at that neuromuscular junction? So what exactly is going on? So in the next picture, we're going to take a look at what's going on. And the steps are kind of labeled here. But let's go through it anyways. They're kind of labeled. So here's the axon terminal again, which is pretty big. And here's the mitochondria, and here's the vesicles. And now we know those little green things are actually the neurotransmitter. So what happens, the first thing that happens is an action potential comes down the axon. And where is it coming from, that action potential? Yeah, the brain or the spinal cord. So that's where it's initiated. The brain or the spinal cord. It travels down, and when it gets to the axon terminal, it causes the vesicles to fuse with the plasma membrane and release the neurotransmitter. So it causes exocytosis. And then the neurotransmitter gets released into this thing, which is called the synaptic cleft. So if you look at this little white line is supposed to be the sarcolemma. Remember the plasma membrane of the muscle cell. This is the muscle cell. But you'll notice there's a gap between the axon and the skeletal muscle cell. There's a gap. They call that the synaptic cleft. And in this cleft is like this gel-like substance, kind of like a sea of gel. So when these neurotransmitters get released, they kind of just float throughout this gel-like substance. Now remember, these are chemicals, so they don't have like little motors on them to motor their way across to this. This is called a receptor. It's actually just a protein wedged in the plasma membrane of the skeletal muscle cell. But it has a special binding site for acetylcholine. So how does it get across? Well, chemicals move by something called Brownian motion, which is just random moving of chemicals. So if you flood enough chemicals into this cleft, some of them are going to find their way to the receptor and bind. Some of them are, just by chance. So how many chemicals do get released? Well, every time you've got a nerve impulse, you have about 60 synaptic vesicles fusing and releasing their contents. So think about this. For every nerve impulse, you get 60 synaptic vesicles undergoing exocytosis. So 60 vesicles are going to release their contents into this cleft. So this is only showing you 1, 2, 3 vesicles releasing their contents. How many molecules of acetylcholine do you think are in each vesicle? Yeah, I mean, according to this, 1, 2, 3, 4, 5, there's actually 10,000 molecules of acetylcholine in every synaptic vesicle. So each one of these has 10,000 acetylcholine molecules. So I'm not going to ask you that number. I'm just kind of giving you an idea. So then how many molecules of acetylcholine are released every time you have a nerve impulse? Okay, so we've got 60 times 10,000, 600,000, yeah. So 600,000 molecules, that's a lot. There are definitely going to be ones that find their way to the other side. And that's kind of what's happening. This is the first kind of step. You get the nerve impulse, you get exocytosis, and all these acetylcholine molecules go into the gap, and they bind here. Okay? Does that make sense so far? Okay, so I know this doesn't give you the answer to how do the filaments slide yet, but this is just the first part.
And then this happens really fast.
It's happened super fast, right? Faster than I can even talk.
Yeah.
Okay, so now I have to get into a little neurophysiology before we move on to the next step, a little neurophysiology. So muscles, when they are at rest, muscle cells, in fact, all your cells when they're at rest are polarized. Polarized. Polar means opposites, like the North and South Pole. So what this means is that when your cells are at rest, and not just muscle cells, they have opposite charges on the inside and outside of the cell. So on the inside of the plasma membrane, when cells are at rest, they have an overall negative charge. On the outside, they have an overall positive charge, like this. And this is true of all cells in your body when they're at rest. That's what you've got. Now, believe it or not, it takes a lot of energy to keep those charges apart because opposites attract. So the positive wants to go where the negative is, and the negative wants to go where the positive is. But what have you got between them? A plasma membrane. So there's a tremendous amount of energy across the plasma membrane of all your cells. And it's keeping the charges apart. In fact, if you took a little voltmeter, which this has actually been done. And you can see the picture up there, and you put a probe into a cell, you could measure the difference in charge across the cell membrane. And that's been done. And that is actually called, well, no, that's not true. You can measure the change in charge across the membrane. Now, this energy across the membrane is not kinetic energy. Remember what kinetic energy is? What is it? Right, when things move, so it's the energy of motion. This is stored energy. What's that called? Potential. So you can measure the stored energy by putting an electrode in, and it's measured as voltage.
So can you explain that again? You said the opposite end?
Yeah, so what's happening here is that the overall charge inside the cell is negative with respect to the outside. The outside's positive. And so these charges want to move towards each other. They want to go towards each other, but there's a plasma membrane between them, and so it takes energy to keep these charges apart. It takes energy, and that energy can be measured if you wanted to with a voltmeter. So keep in mind, all your plasma membranes of all your cells have a tremendous amount of energy across that membrane, and you can measure it. It's measured in millivolts, actually. See the MV there. Does that make sense?
When it's resting is when you're sleeping, or?
No. When it's resting, it means the cell isn't doing something. Okay. So for a muscle cell, what is the cell not doing? It's not contracting, right? Right. Good question. Okay, so if you were to measure the charge across the membrane when it's resting, they call this the resting membrane potential. That's the name of it. And for most cells, we actually know what it is. We know what the resting membrane potential is. So for example, for small neurons, it's like minus 70 millivolts. That's the potential energy. For large neurons, it's minus 90. For skeletal muscle cells, it's minus 80. So that tells you how much energy you have there in the cell. Now you might say next, well, what is causing that? What does that positive even mean? Well, the positive is actually a positively charged particle, and the negative is a negatively charged particle. What do you call a particle that has a charge?
An ion.
Very good, an ion. So that's kind of what these are. These are real chemicals. For example, you could have this ion. Does anyone know what that is? Yeah, potassium, or it could be this. Yeah, or it could even be this. Chlorine, see there's some with negative charges. So that's what's causing this charge, this difference in cells. So the reason you have different charges across the membrane, the reason it's positive on the outside is that there's a greater percentage of positive ions on the outside. And the reason it's negative on the inside is there's a greater percentage of negative ions. So let me give you an example. Let's say that inside the cell, we've got this. So I'm going to give you, this isn't exactly correct, but it's the easiest way to explain it without chemistry. Okay, so this stands for all negative anions. So Cl is called an anion if it has a negative charge. If it's got a positive, it's called a cation. But there's a whole bunch of other negative ones, so I'm just going to put them up like this. So let's make believe this is what's inside the cell. And I'm going to tell you that you've got 2 molecules of this, 1 molecule of this, 5 of this, and 10 of this. Okay, so this isn't exactly how it works, but close enough. So if this has got a +1 charge and you have 2 of them, what's your total plus charge from this? No. +1, you've got 2 of them. +2, right? And then this is +1, you've got 1 of them. +1. Yeah. And then this is -1, you've got 5 of them. Yeah. And this is -2, and you've got 10 of them. -20. Okay, now we're going to add those up to see what our overall charge is inside the cell. So what do we have? -22. So you can see the charge inside is, it's not really -22, but this is how it works. You've got positive ions and you've got negative ones, but when you add it all up, it comes out to negative. Almost ripped my pants there. Now let's say we're on the outside of the cell, and you've got the same ions, same ones, but now you've got this. So this is same ions, different concentration. So now we've got, it's +1. So we got +10, and then +1, +5, -1, -1. This is -2, but we've got 2 of them. Right, -4. So if we add these up, we get +10. See that? So the outside of the cell has an overall positive charge, and the inside has a negative. And the reason is, it's just the grouping of ions. You just happen to have more positive ones on the outside and more negative ones on the inside. Okay, so now you're starting to see actually this is a real thing, these positive and negative charges. So the next question is, well, why is it that way? Why are there more positive charges on the outside, and why are there more negative on the inside? Okay, so let's look at potassium. There's a picture up here with real numbers in it. So this is supposed to be a skeletal muscle cell, which is long and skinny. Is this cell at rest in this picture? Yes. Yes. How do you know that? Yeah. What's that? It's negative on the inside, positive on the outside. It's at rest. Now you can see they have the symbols for all the ions, and they put them in brackets. For when they put a symbol in a bracket, it means concentration of that ion. And what they did is, the bigger the letter, the more the ion there is. So you can see chlorine's really small. It's only got 10. Potassium's really big. It's got 150. But if you wanted to know the real numbers, they've listed them here. So where is potassium in a higher concentration? Inside or outside the cell? Inside. Okay, potassium is the K here. See, it's 150 inside and it's only 5 outside. How about sodium, which is Na? Where is that in a greater concentration? Outside. How about the negative anion, which is A minus? Inside. So the concentrations vary depending. Why do you think there's more potassium inside than outside? Any ideas? What determines what gets in and out of a cell? The cell membrane. So it just so happens the cell membrane is more permeable to potassium, so more gets in. It's not as permeable to sodium, so not as much gets in. Is it permeable to the negative anions? Yes, because there's a lot of them on the inside and there's not a lot on the outside. So that's what sets up the cell so that it has these kinds of charges when it's at rest. It all has to do with the permeability. And this is the way the cell would remain forever unless there's a nerve impulse that's going to change these charges in some way. Now let me just mention one other thing about this electrical field around your plasma membranes is it's pretty big. So several years ago, there was a big concern about high tension power lines. You know, high tension power lines, you know what they look like? Mm-hmm. They're really tall and they usually are crossing a street or they're going up a field or something. And that's, there's a lot of electricity around that, and you might know if you ever drove your car underneath it, what happens to your radio. Yeah, you get static, and that's because the electromagnetic field is interfering with your radio. What if you lived in a home underneath that? You might not get reception, so you might have some interference. So people started noticing, first of all, nobody wants to live under them because it's kind of ugly, kind of, right?
Yeah, because.
Yeah. And so a lot of people don't build their homes there. So instead, schools build their schools there because it's cheap, and who cares? It's not like you're going to live there. But then people started doing studies thinking, well, this electromagnetic field, might it cause problems? And they started looking at the incidence of cancer in children, and they found there was a connection, a correlation, which seemed to indicate that if more kids who went to schools under high tension power lines had more cancer, different types of cancer. So this can happen in statistics. This is a field called epidemiology, where you look at statistics and you try to make connections. And sometimes you can get what's called a spurious connection or spurious correlation, which means two things seem to be related, but they're just not. There was another study that found that the more telephone poles, the more cancer. There's no relationship. However, you can see where people start to think, well, wait a sec, these electromagnetic fields could do something. So this went back and forth, this big discussion. There was a big debate in the public until some biologists said, wait a second, that doesn't make any biological sense, because we know that the magnetic field across our cells is greater than the magnetic field underneath a high-tension power line. So in other words, if that causes cancer, we'd all have cancer, because the field around our own plasma membrane is greater, right? It takes a lot of energy to separate the charge, so you have a lot of field here. So that got debunked, but it was just biology. And if you guys had known about this, you might have figured that out too. So it's no longer an issue, at least that one isn't. So anyways, there's a lot of force here, and they're all caused by how these ions are arranged. So when we say that the plasma membrane is more permeable to potassium and less permeable to sodium, what does it actually mean? Well, you got to look at the plasma membrane, and you have to realize that things cross it in different ways. So one transport process is diffusion, right, which does not require any energy. Then there's active transport, but there are also things like channels. Channels are proteins in the membrane that actually can open up and let things through. So remember that ions, things that have a charge, can't get through the plasma membrane easily. So they often have to travel through these channels. And there are three types of them. One type is called a leaky channel. And this one is always open a little bit, letting things leak in and out. Another type is called a chemically gated channel. It only binds if a specific chemical attaches to it. Another type of channel is called a voltage-gated channel. This is only going to open if the voltage across the membrane changes. Okay, so when these open up, ions can get in, and they do, they move. So let's take a look at what these look like, which might make more sense. See it, a picture of it. So this is an example of a chemically gated channel right here. So you can see this is the plasma membrane right here. Plasma membrane, right? This is the inside of the cell, and that blue part is the outside of the cell. And you can see this is closed. See this channel, like nothing can get through. Now this is the channel. It's a protein. It's wedged in there. See, it's wedged in the plasma membrane. So anyways, this one is closed. Now you can see that potassium can't go through it to get out, and sodium can't go through it to get in. However, if a specific chemical binds to it, all of a sudden the channel opens up. And now potassium can leave and sodium can come in. So a chemically gated channel opens up when a chemical binds to it. Does that make sense?
Yeah.
Why do you think that happens? Why does the binding of a chemical to something cause it to open up?
Because it should be really.
Yes, absolutely. It changes its shape. because if you wedge something into one end of it, another end is going to have to open up to make space for it. So what's the chemical in the situation of the muscle cell that's binding here? No. It's released by the synaptic vesicles. Yes, acetylcholine. Acetylcholine is going to be that chemical. Now what about a voltage-gated channel? Well, same kind of thing. You've got a protein wedged here, and you can see now this one, oh sorry, I didn't move it yet. There we go. Here's the wedged channel, the protein, and you can see that the inside of the cell is negative, the outside is positive. So is this cell at rest, or is it actively contracting? Right, it's at rest. And so when it's at rest, the charge across the membrane is -80. And at -80, this is closed. But what happens in this situation? You can see the charge changed. So now if you put a little electrode in it, it would be +30. And when it's +30, it opens up. And now sodium can come in. So this channel only lets sodium in. So the channel opens and closes when the voltage changes.
Where are you getting the numbers from?
Oh,
30 negative.
I just know them.
Oh, we don't have to know that.
No.
Okay.
No. So this is the thing. You don't have to know them.
Okay.
Every voltage-gated channel opens and closes at a different voltage, and it's known. You don't have to know it. But what I would like you to know is just that.
Okay.
That these open and close at certain voltages. Okay. So, last slide here. So now that the channel's open and closed, the question is, okay, I get that ions move, but why do they move when the channel opens? Just because you open a channel, why do the ions move? Why don't they just stay where they are?
Concentration.
Yeah. Chemicals in a solution will move where? From a low to a high concentration, or will they go from a high to a low? Right. And that's called a chemical gradient. So the reason the ions move is they're moving down their chemical gradient. They're going from a high to a low concentration. Do you need energy to make them move? No, that's called diffusion. So the reason potassium moves out is because it's in a higher concentration inside. And the reason sodium moves in is because it's in a higher concentration outside. So that's why they move. Now there's one other reason they move. They are chemicals, but they also have a charge. And charges like to go to the opposite. So the reason sodium goes in is because it is more negative inside, at least in the beginning. So we say they're moving down their electrical gradient, which means from positive to negative and vice versa. So now if you think about it, they're both chemicals and they have a charge. So we say they're moving down their electrochemical gradient. And that causes them to move really fast because they're moving for two reasons. Does that make sense so far? This part. This is really tricky, actually, and I'm trying to make it as clear as possible. But you should read your book on this part because it might help reinforce it. So we'll continue on with this on Friday. And Friday, make sure you bring your atlas because we're going to look at muscles again one more time.
So there is school Friday. We don't celebrate.
No, we don't. Just public high schools do, but not colleges.
We don't have a free lab, do we?
Nope, because you already did it.